Before electricity, before diesel, before the internal combustion engine transformed rural America, there was a beast of fire and iron that changed everything: the portable steam engine. By 1900, over 50,000 steam engines worked American farmland. Machines weighing up to 6 tons that could generate the power of 40 horses while consuming entire cords of wood daily. Yet in 1869, when J.I. Case perfected his portable design, most farmers still relied on animal muscle and back-breaking labor to thresh grain, saw timber, and pump water. These roaring titans didn't just mechanize agriculture, they announced the arrival of the industrial age to fields and prairies. This is the story of the Case portable steam engine, the innovation that transformed it from stationary factory equipment to mobile rural powerhouse, the engineers and farmers who operated these iron giants, and the dangerous, magnificent era when steam ruled the heartland. Picture a Wisconsin wheat field in 1868, harvest time. 30 men swing flails in rhythmic unison, separating grain from chaff through sheer muscular repetition, the same method farmers had used for 3,000 years. Each man might thresh 7 bushels in a 10-hour day. The work destroyed backs and shoulders, yet America's expanding population demanded more grain than human hands could process. Meanwhile, in eastern factories, stationary steam engines had been revolutionizing manufacturing for decades, their pistons driving machinery with tireless precision. But these cast-iron leviathans sat bolted to foundations, fed by permanent boiler rooms, useful for textile mills, useless for farms where work moved with seasons and fields. The breakthrough wasn't inventing steam power, it was making it movable. Jerome Increase Case had been building threshing machines in Racine since 1842, watching farmers struggle with horse-powered separators that required 8 to 12 animals walking endless circles. He'd experimented with mounting steam engines on wheeled chassis before, but early attempts proved too heavy, unstable, or prone to boiler explosions. The engineering challenge was formidable: create a boiler compact enough to move, yet large enough to maintain sufficient pressure. Design a firebox that could burn varied fuels from cordwood to straw. Mount everything on wheels that wouldn't sink in soft soil, and make it simple enough for farmers, not trained engineers, could operate it safely. By 1869, Case had solved it. His portable steam engine weighed 6,000 pounds, small enough to be hauled between farms by horse teams, yet powerful enough to drive threshing machines, sawmills, and feed grinders. The heart was a vertical fire tube boiler standing 5 feet tall, containing dozens of tubes through which hot gases passed, heating water that surrounded them. At 100 pounds per square inch, this superheated steam possessed enormous potential energy, channeled through valves to a horizontal cylinder where it pushed a piston back and forth. That reciprocating motion turned a massive flywheel, 4 feet across, weighing several hundred pounds, which smoothed the power delivery and drove a belt pulley at a steady, controllable speed. The genius lay in the details. Case used wrought iron plates riveted together for the boiler shell, stronger and more reliable than the cast iron competitors favored. He positioned the firebox below and slightly behind the boiler, creating better draft and allowing longer wood lengths. The engine sat on a sturdy oak frame reinforced with iron, mounted on cast iron wheels with 4-inch wide faces to distribute weight. A simple governor, 2 weighted balls spinning on arms, automatically regulated engine speed by controlling steam admission, preventing dangerous runaways when load varied. This wasn't merely a machine, it was freedom from biological limitations, the promise that one man could accomplish what previously required dozens. Stand before a Case portable for the first time and your eyes struggle to comprehend the assembly. The vertical boiler dominates, a cylindrical tower jacketed in polished sheet metal, its surface dotted with rivets like geometric constellations. Atop sits the steam dome, a bell-shaped crown where the driest steam collects before entering the engine. Below, the firebox door glows orange during operation, a rectangular gateway to controlled inferno. But understanding this machine requires examining each component as farmers did, practically, with an eye toward function and failure. The boiler contained the essential transformation. Inside that iron shell, 150 gallons of water surrounded 48 2-inch fire tubes running vertically from firebox to smokebox. Hot gases from burning wood roared upward through these tubes, transferring heat to water, then exited through the smokestack, a 6-foot-tall pipe that created draft and announced the engine's presence for miles. Every square inch of tube surface area was a heat exchanger, and case engineers had calculated the perfect balance between heating surface, water capacity, and steam space. Too small and you couldn't maintain pressure under load. Too large and you wasted fuel heating unnecessary water. 3 glass gauge tubes mounted at eye level showed water level with absolute clarity, the operator's most critical reference. Let water drop below the crown sheet, the top plate of the firebox, and catastrophe followed. Exposed metal would overheat, weaken, and rupture, releasing 150 gallons of boiling water and superheated steam in an explosive blast. 2 independent injectors, clever devices that used steam pressure itself to force cold water into the hot boiler, provided redundant water supply, fed from the wooden water tank mounted on the engine frame or from barrels hauled alongside. The steam engine proper sat horizontally, its cylinder a precision-bored tube 8 inches in diameter. Inside, a piston fitted with spring-loaded rings sealed against cylinder walls as steam pressure drove it back and forth in 4-foot strokes. A piston rod connected to a crosshead, sliding in guides, converting linear motion to rotary through a connecting rod attached to a crankshaft. The engineering elegance lay in the valve gear, Stephenson's link motion, borrowed from locomotives, which allowed the operator to control not just engine speed but direction, essential for powering reciprocating sawmill blades or adjusting belt tension. That massive flywheel served multiple purposes: momentum storage, smoothing power pulses between piston strokes, and providing the belt pulley. Wrapped around this pulley ran a leather belt, often 80 feet long, 10 inches wide, pieced together with rawhide lacing that transmitted power to whatever machine needed driving. This belt, simple as it seemed, represented the crucial interface between stationary steam plant and mobile agricultural equipment. Dawn breaks over a Michigan wheat field in August 1875. The threshing crew, 12 men, has arrived with the steam engine, hauled overnight by 6 draft horses from the previous farm. Now comes the morning ritual, precise as liturgy, where mechanical giant transforms from cold metal to living power. The engineer, a wiry man named Thomas Brennan, begins his checklist, movements practiced through 5 harvest seasons. First, inspection. He circles the engine, checking every nut, bolt, and cotter pin. Vibration loosens fasteners. One missing linchpin could drop a wheel at full operation. He examines the belt, looking for worn spots or cracked lacing. His hands probe the packing around the piston rod, feeling for steam leaks. He opens the manhole cover atop the boiler, a circular plate held by multiple bolts, and inspects inside with a lantern, looking for scale buildup on tube surfaces or corrosion on plates. Satisfied, he closes and seals it, then signals his water boy, a 15-year-old named Raymond. They hand pump 150 gallons from barrels, filling until the glass gauges show water at proper level, well above the firebox crown. Now, kindling. Brennan crumples newspaper, adds pine shavings, arranges split oak kindling in a careful pyramid inside the firebox. He strikes a match, touches it to paper, watches flame catch and spread. Once kindling burns steadily, he adds larger splits, building heat gradually. Rush this step and you risk thermal shock. Cold water meeting rapidly heating metal can crack boiler plates. He wants a gentle temperature rise over 30 minutes. While fire builds, he oils everything. A long-spouted oil can in hand, he feeds linseed oil to every bearing, the main crankshaft bearings, the crosshead guides, the governor pivot points, the eccentric straps that drive the valve gear. Steam engines run at 200 RPM under load. That's 12,000 revolutions per hour. Without proper lubrication, brass bearings would seize in minutes, welding themselves to steel shafts with frictional heat. Smoke begins pouring from the stack now, white-gray from burning oak. Brennan adds larger splits, building the fire deliberately. He opens the blower valve slightly, directing steam from the growing pressure into the smokestack base, creating additional draft to intensify combustion. The boiler creaks and ticks as metal expands. He watches the pressure gauge, a Borden tube dial, as the needle creeps upward. 20 pounds, 40, 60. At 80 pounds, he performs his first steam blow. Opening the cylinder cocks, small valves that vent the cylinder, he cracks the throttle briefly. Steam hisses and roars, clearing any condensation from the cylinder. He closes the cocks, watches pressure rebuild to 100 pounds, working pressure for a case portable. The pop-off safety valve sits ready at 110 pounds, a final protection against overpressure. Raymond has meanwhile positioned the threshing machine, a JI Case New Eclipse, 30 feet distant, angled properly for wind to carry chaff away. Other crew members stretch the belt between engine pulley and separator pulley, measuring carefully. Too tight and it wastes power, too loose and it slips, generating friction heat that can ignite the leather. Brennan pulls the throttle gradually. The flywheel begins turning, slowly at first, then faster as steam fills the cylinder in rhythmic pulses. The entire machine vibrates with contained power. The belt tightens and begins running, turning the separator's main shaft. Men position the first wheat bundles. Another day begins. The ritual took 90 minutes. Getting it wrong could kill everyone present. Once running, the steam engine became the heartbeat of the operation, and every crew member synchronized to its pulse. At full throttle, the case portable turned 200 RPM, that 4-foot flywheel completing over 3 revolutions per second. The leather belt, tanned cowhide stitched with rawhide thongs, raced around its circuit at over 2,000 feet per minute, a loop of controlled violence that could snatch clothing, break bones, or decapitate the careless. The engine's constant chuff, 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 exhaust steam venting through the smokestack, provided the tempo for the entire harvest operation. Brennan, the engineer, stood at his post beside the engine throughout the day, one hand always near the throttle, eyes continuously scanning his domain. He watched the steam pressure gauge, adjusting fire and water to maintain exactly 100 pounds. He listened to the engine's voice, the rhythm of piston strokes, the hiss of steam, the slap of valve gear, detecting problems by sound before gauges registered them. A slight knock might mean the crosshead needed adjusting. A whistle at the piston rod meant packing failure. A grinding growl from the governor indicated bearing wear. Every 15 minutes, his water boy, Raymond, scrambled atop the engine frame with a long-spouted oil can, feeding lubricant to cylinder steam chests through special sight-feed lubricators, glass reservoirs where oil droplets could be counted, ensuring proper feed rates. Steam engines consumed oil prodigiously. The high temperatures turned lubricant to smoke, requiring constant replenishment. Run dry for even minutes, and bearing babbitt, soft metal designed to protect harder steel, would melt and fail. The firebox demanded constant attention. Oak burned fast when forced by steam draft. Brennan fed split wood every 10 minutes, maintaining a hot, even fire. He learned to read the smokestack. Black smoke meant incomplete combustion, wasting fuel. Clear smoke meant efficient burning but risked dropping steam pressure. The ideal was barely visible gray, hot gases efficiently transferring energy to boiler water. On windless days, smoke hung thick over the field. Crews worked half-blind, throats raw, eyes streaming. At the separator, men worked in specialized roles orchestrated by the belt's relentless motion. Bundle pitchers forked wheat sheaves onto the feeder conveyor, demanding precise timing to avoid choking the machine. The separator man controlled feed rate with a hand lever, watching for slugs of grain that could jam cylinders. Two baggers worked the grain spouts, switching empty bags for full ones in continuous rotation, each bag weighing 60 pounds when filled. Strawbacks forked threshed straw away from the blower, building stacks or hauling to feeding stations. Every man understood viscerally. The engine never tired, never slowed, never sympathized. The belt ran continuously at killing speed. Feed bundles too fast, and the separator would choke and stall, snapping the belt or shearing drive pins. Let it run empty, and you wasted precious steam, burning fuel for no purpose. The rhythm, feed, thresh, bag, stack, had to flow without pause from dawn until dark, or profits evaporated in wasted time. Problems arose constantly, testing Brennan's experience. The belt might stretch from heat and humidity, requiring repositioning of separator or adjustment of belt tightener. A boiler tube could leak, detected by water level dropping faster than normal, forcing shutdown for plugging or repair. The governor might stick, sending engine speed surging dangerously high until Brennan slammed the throttle closed. Clinkers built up in the firebox, choking grates, requiring raking while maintaining steam, a delicate, dangerous operation. Mid-afternoon brought the water crisis that tested every operation. The barrels were empty. Raymond and another boy drove the wagon a quarter-mile to the creek, filled from a slow-moving stream, returned. 20 minutes lost, steam pressure dropping to 70 pounds as Brennan conserved water. The separator slowed, men stood idle, farm owner paced anxiously. When water arrived, Brennan worked both injectors furiously, rebuilding pressure while fire roared. The delay cost them 90 bushels of threshing time, roughly $5 in 1875 currency, significant money. As sunset approached, exhaustion permeated the crew. 12 hours of continuous operation, standing, lifting, watching, feeding fire, carrying bags, breathing dust and smoke. Yet the engine ran on, tireless, requiring only fuel and water, its mechanical precision unchanged from morning. This was the revolution, human limits versus mechanical endurance. When darkness finally forced shutdown, Brennan reduced fire gradually, closing drafts to let coals die slowly. He couldn't simply abandon hot boiler. Uneven cooling could warp plates or crack welds. He maintained light pressure for an hour while metal cooled evenly, performing end-of-day maintenance by lantern light, cleaning ash from firebox, draining condensation from cylinders, checking every bolt again. Tomorrow, they'd begin again. The genius of the Case Portable wasn't just generating power, It was delivering that power anywhere farmers needed it. Unlike factory engines bolted to foundations, these 6,000-pound machines traveled constantly, hauled across rutted roads, through creek fords, up hillsides, bringing industrial force to remote fields. This mobility created its own engineering challenges and daily dramas that separated skilled engineers from amateurs. Transporting the engine required a dedicated horse team, typically 6 draft animals, and elaborate preparation. The engine sat on its own wheels, essentially a trailer, but those 4-inch-wide cast-iron wheels weren't designed for road travel. They excelled at distributing weight on soft soil, but had no suspension, no springs, no give. Every bump transmitted directly to the boiler and frame. Cross-country travel risked cracking boiler tubes from vibration, loosening rivets, or fracturing the cast-iron wheels themselves on rocks. Smart engineers like Brennan took precautions. Before moving, he drained the boiler completely. 150 gallons of water added 3/4 of a ton to already substantial weight. He removed the smokestack, laying it horizontally in a rack, preventing the tall pipe from catching tree branches or swaying dangerously. He tied down the belt and tools, securing everything that could shift. Most critically, he blocked the flywheel with wooden wedges, preventing it from rotating during transport. An unsecured flywheel could build momentum on downhill stretches, destroying gearing and snapping the crankshaft. The horse team required patient, powerful animals, Percherons or Belgians, draft breeds weighing 1,800 pounds each, accustomed to heavy pulling. 6 horses in tandem could move the engine across flat ground at perhaps 2 miles per hour, but hills required doubling teams, 12 horses straining in harness. Descending was worse. Horses couldn't hold back 6 tons on steep grades. Engineers chained one wheel, creating drag, or used the engine's weight transfer brake, a hand-operated screw that pressed wooden blocks against wheel rims, heating them to smoking. River crossings presented calculated risks. Bridges built for farm wagons might collapse under concentrated engine weight. Brennan learned to evaluate bridges by examining beams and listening to how they creaked under the horse's weight before committing the engine. Some rivers required fording. He'd ride ahead, probing depth with a pole, checking bottom firmness. Soft mud could trap wheels. Fast current could unbalance the top-heavy machine. More than one engine ended up waterlogged in creek beds, requiring days of block-and-tackle recovery. The arrival of an engine at a new farm became a community event. Word spread that the steamer was coming. Neighbors gathered to watch. Children stood at safe distance, eyes wide as the iron giant rolled into the yard, horses snorting, engineer walking alongside with goad, directing placement. Positioning mattered enormously. Distance from separator, prevailing wind direction, proximity to water supply, clearance from buildings for fire safety. Brennan typically spent an hour on placement, using a surveyor's level to ensure the engine sat flat. Tilting risked uneven water coverage of firebox plates or oil pooling away from distribution points. Some larger operations invested in self-propelled engines, steam traction machines that eliminated horse teams by using the engine's own power for mobility. These magnificent beasts featured additional gearing that transmitted power to large rear drive wheels, often 6 feet in diameter, with steel cleats for traction. A chain and sprocket system, borrowed from locomotive practice, turned wheels at perhaps 3 miles per hour. One man could guide a 20-ton traction engine across country using only throttle and steering wheel. But self-propulsion created new hazards. Traction engines were ungovernable on steep descents. More than one engineer watched helplessly as his runaway machine picked up speed, steering useless, until it crashed into fences or ditches. The complex gearing added failure points. Chains broke under load, whipping across operators' positions. Cleated wheels destroyed roads, earning farmers ire. Many engineers preferred the simpler, portable design, accepting the inconvenience of horse teams over the risks of self-propulsion. By 1880, networks of custom operators emerged, independent engineers who owned engines and hired out complete threshing outfits. These men traveled circuits, each serving 20 to 30 farms per season, hauling equipment hundreds of miles over summers. They became legendary figures in rural communities, names like Steam John Anderson or Boiler Tom McCarthy, known for their skill, reliability, and occasional spectacular failures. Their arrival meant harvest could proceed. Their reputation meant the difference between successful seasons and disaster. The Case Portable represented controlled power, but control was always temporary, always conditional, always dependent on human vigilance and mechanical integrity. Between 1870 and 1900, steam engine explosions killed over 2,000 Americans, maiming thousands more. Farm engines operated by minimally trained crews in remote locations contributed disproportionately to these statistics. Every engineer knew men who died. Many carried scars from their own near misses. Boiler explosions were the nightmare scenario. At 100 pounds per square inch, water inside the boiler exerted enormous pressure on every rivet and seam. The entire structure contained approximately 50,000 BTUs of thermal energy, equivalent to 10 pounds of dynamite. If the pressure vessel failed suddenly, that energy released instantaneously. Witnesses described explosions as earthquake-like, a deafening roar, a pressure wave that knocked men flat, a cloud of superheated steam that scalded everything within 100 feet. The boiler itself might rocket skyward, clearing trees, or split and peel like a banana, sending jagged iron fragments through anyone nearby. The most common cause was low water, allowing water level to drop below the firebox crown sheet. Exposed metal, no longer cooled by water contact, reached cherry red temperatures in minutes. At this point, structural integrity vanished. The thin steel plate simply gave way, and 150 gallons of boiling water flashed instantly to steam, expanding 1,600 times in volume in a fraction of a second. The resulting pressure spike exceeded any safety valve's capacity. How did low water happen? Sometimes engineer negligence, drunk on whiskey, asleep, distracted. More often, mechanical failure. Glass gauge tubes might clog with sediment, showing false water levels. Injectors could fail from plugged strainers. Unseen leaks might drain water faster than normal. Some engineers, pressured to maintain steam pressure for maximum output, ran water dangerously low, gambling that they could maintain the delicate balance. Some lost that gamble. James Patterson, engineer for a custom threshing outfit in Iowa, died in September 1882 when his Case Portable exploded near Morning Sun. Witnesses reported the engine had been running normally, threshing steadily, when suddenly the boiler burst like a thunderclap. Patterson, standing at his usual position, was killed instantly by flying metal. 2 crew members sustained severe steam burns. Investigation revealed a clogged gauge glass. Patterson had been running for hours with no water visible, not realizing the actual level had dropped critically low. His widow received no compensation. He'd worked as an independent contractor. Belt accidents maimed more men than explosions, though less spectacularly. That racing leather band appeared almost innocuous compared to roaring boilers and spinning flywheels, but it ran continuously at 30 miles per hour, invisible in speed, catching anything that touched it. Loose clothing would snag, then wrap, pulling the victim into the moving belt where they'd be crushed against pulleys or gears. Arms were torn off, bodies broken. Most engineers could recount seeing it happen. One moment a man standing normally, the next instant jerked into the machinery, the horrible grinding sound, the blood. Prevention meant constant vigilance about clothing. Engineers wore tight-fitting shirts, buttoned collars, pants legs stuffed into boots, no dangling suspenders, no loose sleeves, no untied bootlaces. But exhaustion bred carelessness. After 12 hours in heat and dust, men's attention wandered. A moment's inattention reaching across the belt, a shirt tail that had worked loose, and tragedy followed. Flywheel bursts were mercifully rare but catastrophically destructive. Cast iron wheels spun at 200 RPM stored tremendous kinetic energy. Flaws in casting, inclusions, voids, cracks, might weaken the structure invisibly. Under centrifugal stress, a weakened wheel could disintegrate, sending iron fragments outward at projectile velocities. One incident in Wisconsin in 1879 saw a burst flywheel kill 4 men instantly and wound 6 others, some standing 50 yards distant. The explosion scattered iron pieces across a quarter-mile radius. Investigators found one fragment embedded 3 inches deep in an oak tree. Burns were omnipresent. Steam pipes carried 340-degree vapor. Touching one meant instant deep tissue damage. Firebox doors radiated intense heat. Opening them to add fuel risked facial burns. Hot ash and coal raked from fireboxes started grass fires regularly. Smart engineers kept water buckets handy and worked carefully, but accidents happened. Most veteran engineers bore scar patterns, mottled patches on forearms from steam leaks, fingertips slickened from burn contractures, perhaps a milky blind eye from a splashed drop of boiling water. Why did men persist? Economic necessity drove most. A skilled engineer earned $3.50 to $5 per day, excellent money in 1880 when farm laborers made $1 per day. This wage could support families, purchase land, build futures. Men also took fierce pride in their skills. Operating steam engines required intelligence, mechanical aptitude, split-second decision-making. Engineers were craftsmen, specialists, respected in communities for knowledge and competence. The danger was the price of status. Some engineers treated risks cavalierly, performing reckless acts to demonstrate courage or impress observers. Wildcat engineers would run pressures above rated limits, disable safety valves for more power, or operate with insufficient water, unnecessary risks taken for bravado. These men died disproportionately and killed crew members with them, giving steam engines their fearsome reputation. Behind every steam engine stood not individuals, but crews, teams of 10 to 15 men who lived and worked together through harvest season, forming temporary communities bound by shared labor, danger, and purpose. Understanding the portable steam engine era requires knowing these men, who they were, how they lived, what motivated them beyond paychecks. The engineer stood atop the hierarchy, skilled, responsible, usually older. Many had trained as machinists or millwrights, bringing formal mechanical knowledge. Some had learned through apprenticeship, working seasons as firemen, assistant engineers, before earning engineer positions. This role demanded more than technical skill. A good engineer managed crews, negotiated with farmers, maintained equipment, and made countless daily decisions affecting safety and productivity. Engineers like Thomas Brennan were known by reputation across counties. Farmers specifically requested them. The fireman, not a firefighter, but the engineer's assistant, handled firing the boiler and general labor. Usually young men, 17 to 25, seeking to learn the trade. Firemen fed wood, cleaned fireboxes, hauled water, and absorbed practical knowledge. After several seasons, experienced firemen might purchase or lease their own engines, becoming independent operators. This position was apprenticeship, pathway to better futures. Many successful engineers started carrying wood as teenagers. The separator tender controlled the threshing machine, understanding its mechanical complexities. He adjusted feed rates, monitored bearings, listened for jams, and performed field repairs. An expert separator man could coax maximum performance from worn equipment, while an amateur could destroy expensive machinery in hours through ignorance. This position required different knowledge than engine operation, understanding of grain handling, chaff separation, the behavior of straw and wheat, making the separator tender and engineer equal partners in the operation. Bundle pitchers, 6 to 8 men, worked the hardest physically. They forked wheat sheaves from shocks in the field, loaded wagons, and fed bundles into the separator continuously. This was brutal labor, lifting 60-pound sheaves overhead repeatedly, working in suffocating dust and chaff, maintaining relentless pace. These positions were filled by farm boys seeking seasonal wages, drifters moving from farm to farm, or the farm owner's sons. Turnover was high. Men quit from exhaustion or injury, requiring constant replacement. Baggers handled threshed grain, hot, dusty work requiring endurance and timing. Each bag weighed 60 pounds when filled. Baggers switched full for empty dozens of times hourly, hefted filled bags onto wagons, then stacked them. Young men built powerful physiques doing this work, but injuries were common: back strains, crushed fingers, hernias. The work paid better than bundle pitching, reflecting the skill needed to maintain constant flow without jamming spouts. Water boys, typically 14 to 16 years old, hauled water from sources to engine, maintaining the 50-gallon-per-hour consumption. They drove wagons, operated hand pumps, and assisted engineers with minor tasks. This was often boys' first paid work, introduction to adult labor. Veterans recalled waterboy days nostalgically, part of the crew but spared the most dangerous work, learning by observation, earning pocket money while surrounded by the greatest machines they'd known. The cook, often the only woman on site, sometimes the farmer's wife or a hired professional, fed the crew. Steam threshing demanded enormous caloric intake. Men might consume 5,000 calories daily. The cook prepared 3 hot meals: pre-dawn breakfast, eggs, meat, potatoes, bread; noon dinner, the main meal, roasts, vegetables, pies; and evening supper. She worked from before dawn until evening, managing wood-fired stoves and feeding 15 hungry men. Her role was essential. Good food kept crews working efficiently, while poor meals caused grumbling and turnover. Crews developed intense camaraderie during season-long partnerships. They worked 12 to 14 hours daily, 6 days weekly, through summer and fall. Many slept in barns or granaries, sometimes in tents near the engine. They shared meals, exchanged stories, developed in-jokes and nicknames. Veteran crews worked with practiced coordination, communicating through gestures and abbreviated shouts over machinery noise. New members were tested, hazed, then gradually accepted as they proved competence and reliability. The social dynamics resembled military units or ship crews, hierarchical but interdependent, with mutual respect earned through demonstrated skill and endurance under pressure. Engineers held authority, but smart ones listened to experienced crew members. Arguments erupted over work pace, break timing, fair load distribution, but serious conflicts were rare. The work demanded cooperation. Many men returned to the same crews year after year, timing their lives around harvest season. They might farm their own land or work other trades during winter, but come July, they rejoined their threshing crews. These partnerships became fundamental to their identities. Decades later, elderly men recalled their threshing days with vivid detail and evident pride. The camaraderie, the satisfaction of productive work, the feeling of mastery over powerful machines. For young men, particularly farm boys constrained by limited horizons, threshing crews offered adventure, traveling across counties, operating magnificent machinery, earning substantial wages, demonstrating courage and competence. The danger was acknowledged but romanticized. Men competed informally to work closest to the engine, handle the most demanding positions, show indifference to risk. This bravado was simultaneously life-threatening and binding. Shared risk forged trust. The 1869 Case portable wasn't static technology, it evolved continuously through decades of innovation, competition, and hard-won lessons. By 1900, steam engines barely resembled their ancestors, though core principles remained unchanged. This evolution, driven by engineering ingenuity and brutal market competition, transformed portable engines from promising novelties into refined powerhouses. The immediate improvements focused on efficiency. Early engines wasted tremendous fuel through poor insulation and inefficient combustion. By 1875, Case and competitors like Altman-Taylor and Russell were wrapping boilers in wooden lagging packed with asbestos insulation, dramatically reducing heat loss. The fuel savings were substantial, perhaps 30% less wood for equivalent output, making the difference between profitable and unprofitable operations. Boiler design advanced significantly. The original vertical fire tube layout gave way to horizontal return tubular boilers, longer, lower, with larger heating surfaces. Water tube boilers, where water circulated through tubes surrounded by hot gases, appeared by the 1880s, offering faster steam generation and greater safety. Some designs incorporated superheaters, additional tubing that dried and heated steam above its saturation temperature, increasing thermal efficiency by 15 to 20%. The safety crisis drove regulatory innovation. After numerous catastrophic explosions, states began requiring boiler inspections and engineer licensing. By 1885, most engineers needed certificates demonstrating competence issued after examination by state authorities. Boiler manufacturers faced new standards: minimum plate thickness, mandatory safety valves, required pressure gauges, and steel construction specifications. These regulations reduced explosion rates significantly, though they never eliminated them entirely. Portability evolved dramatically with self-propulsion. The 1880s saw widespread adoption of traction engines, steam power plants that moved themselves via geared drive wheels. Companies like Case, Huber, and Minneapolis Threshing Machine competed fiercely in this market, each claiming superior traction, reliability, and power. Traction engines featured differential gearing, allowing turns without wheel slippage, and reversible operation for maneuvering. Sizes grew enormous. By 1900, some traction engines weighed 20 tons, generated 110 horsepower, and cost $2,500, 3 years' wages for farm laborers. But complexity bred problems. Traction engines' additional gearing meant more failure points, expensive repairs, and specialized knowledge requirements. Their weight destroyed roads and bridges, creating legal conflicts with townships. Fuel consumption was voracious, sometimes a cord of wood per hour under full load. Many farmers reverted to simpler portable designs pulled by horse teams, accepting mobility limitations in exchange for reliability. Competitive market drove continuous refinement. By 1890, dozens of manufacturers battled for market share. Case, Altman-Taylor, Advance Rumilly, Minneapolis, Buffalo Pits, Russell, Huber, Frick, Nichols and Shepard, and many others. Each year brought new features: improved governors for steadier speed, compound engines using steam twice at different pressures for efficiency, balanced valve gear for smoother operation, better lubrication systems. Advertising became fierce. Manufacturers issued lavish catalogs claiming superior power, fuel efficiency, reliability. Demonstrations at state fairs and field trials became competitive spectacles. Engines tested side by side, pulling heavy loads, maintaining pressure, consuming measured fuel amounts. Farmers attended these events like sporting competitions, allegiances forming around favorite brands. Casemen scorned advance men, each certain of their chosen brand's superiority. World War I accelerated development, while simultaneously presaging steam's doom. Military demand for transportation led to improved internal combustion engines, initially gasoline, then diesel. These engines offered power-to-weight ratios steam couldn't match. Instant startup versus steam's hours-long preparation, and dramatically reduced operating complexity. Trucks and tractors began appearing on farms by 1915. Yet steam persisted through the 1920s, particularly for heavy stationary work, sawmills, feed grinding, silo filling. Some farmers loyal to steam operated their engines into the 1930s, maintaining machines decades old through skill and determination. The Depression made new equipment purchases impossible. Aging steamers continued working because they represented paid-for capital, repairable with blacksmith skills rather than expensive parts. The transition was gradual, regional, and often grudging. Older engineers particularly resisted change, their identities bound to steam knowledge. Younger men embraced tractors' convenience despite acknowledging steam's raw power advantage. By 1940, operating steam engines were museum pieces or hobbyist curiosities, the knowledge slowly dying with the generation who'd worked them. Engineering societies recognized this loss. The American Society of Mechanical Engineers, founded in 1880 largely by steam engineers, began documenting portable engine technology in detail during the 1930s, interviewing aging engineers, photographing surviving machines. They understood that irreplaceable knowledge was vanishing with every funeral. Today, perhaps 10,000 portable steam engines survive in America, scattered across farm museums, historical societies, private collections, and forgotten barn corners. These machines, once commonplace as pickup trucks, now represent vanished ways of working and thinking. Their preservation and occasional operation keep alive more than mechanical artifacts. They maintain connection to the knowledge, skills, and culture of the steam era. The survival rate was surprisingly low. When diesel and gasoline tractors replaced steam, most engines were simply abandoned, left in fields where they sat until scrapped during World War II metal drives. Their substantial iron was valuable. Thousands were melted down from munitions. Others rusted away, exposed to weather, disintegrating slowly. Some were cannibalized for parts to keep dwindling fleets operational. By 1950, steam engines had become nearly worthless. Farmers sold them for scrap prices or gave them away. The preservation movement began in the 1950s, driven by nostalgia and historical awareness. Men who'd worked steam as young men, now elderly, began collecting engines, restoring them to operation, and demonstrating them at newly formed threshing reunions. These events, combining county fair, historical reenactment, and social gathering, emerged across the Midwest. Annual celebrations where restored engines powered antique separators, demonstrating lost techniques to curious crowds. The Case 65-horsepower traction engine at the Stew Museum in Grand Island, Nebraska, represents this preservation ethic. Built in 1912, it threshed wheat across Nebraska and Kansas until 1938, then sat abandoned until 1967 when enthusiasts rescued it and restored it. Today, it operates annually at the museum's threshing demonstration, its flywheel spinning, belt running, separator processing grain exactly as it did a century ago. Watching it operate provides visceral understanding impossible through photographs or descriptions, the scale, noise, power, coordination required. Private collectors maintain functional steam engines, though operating them is increasingly challenging. Insurance companies view them as extreme liability risks. Finding venues willing to host demonstrations grows difficult. The knowledge required to operate safely is specialized and fading. Modern engineers understand principles but lack the practical, intuitive understanding that came from years of daily operation. Starting and running a steam engine safely requires apprenticeship-style training, increasingly hard to obtain. The engineering sophistication of these machines surprises modern observers. Examining a preserved case portable reveals remarkable precision. Perfectly bored cylinders, fitted valves, precisely calculated spring tensions. This was pre-computer-aided design engineering, relying on empirical testing, mathematical calculation, and machinist's art. The fact that century-old engines still operate when properly maintained testifies to original design quality. Museums struggle with interpretation. How do you convey the danger, exhaustion, and skill to visitors accustomed to push-button convenience? Static displays fail to communicate the reality. Operating demonstrations help but sanitize the experience. Volunteer operators work 4-hour shifts, not 12-hour days. Safety regulations prohibit many period-accurate practices. Observers watch from safe distances, missing the intimacy and risk of actually working aboard a machine. Some museums address this through first-person interpretation. Costumed demonstrators adopt engineer personas, explaining decisions, pointing out dangers, sharing the knowledge. The best interpreters are often elderly men who actually worked steam commercially, their explanations enriched by authentic experience. As this generation dies, the last American who commercially operated farm steam engines likely died in the early 2000s. This living connection vanishes forever. The artifacts persist, but context fades. What did the belt sound like running? How did you judge when fire needed feeding by flame color? What did the distinctive smell of hot cylinder oil mixed with coal smoke and wheat chaff actually smell like? These sensory details, crucial to the work, can't be fully archived. Each death of a steam engineer represents permanent loss of irretrievable knowledge. Yet the surviving machines themselves speak eloquently. Run your hand along a boiler's rivet seams, feeling how they're spaced and sized, each a calculation of stress and safety. Examine the governor's weighted balls, understanding how their simple elegance automatically controlled tremendous power. Study the valve gear's intricate linkages, tracing how reciprocating motion translates to rotary, how timing and reversing are mechanically accomplished without electronics. These machines are physical embodiments of engineering thought, teaching engineering principles through their very existence. Stand in a modern grain field where a combine harvester, GPS-guided, air-conditioned, processing acres per hour, works effortlessly. The contrast with steam threshing seems absolute, then versus now, primitive versus advanced, exhausting versus comfortable. Yet direct lines connect that combine to the case portable of 1869. The steam era didn't just precede modern agriculture, it made modern agriculture conceptually possible by demonstrating that mechanical power could replace muscle, that mobility and power could coexist, that farmers could be engineers. The lessons learned during steam's reign shaped everything that followed. Engineers discovered optimal power transmission methods, belt drives, direct gearing, shaft systems. Through steam-era experimentation, they learned mobile power plant design, weight distribution, cooling requirements, fuel efficiency, operator safety. They established maintenance practices, operator training methods, and safety regulations. The tractor engineers of 1910 weren't inventing from nothing. They were applying decades of accumulated knowledge from steam operations. The cultural transformation was equally profound. Before portable steam engines, farming was fundamentally biological, constrained by animal and human muscle. Farmers thought in terms of how many horses they could afford, how many men they could hire. Steam broke this constraint, introducing a new vocabulary and mindset: horsepower ratings, fuel efficiency, mechanical maintenance. Farmers became machine operators, calculating costs per acre, comparing technologies, making capital investment decisions. This mental shift from biological to mechanical agriculture began with steam and never reversed. The human cost deserves acknowledgement without romanticism. The men who operated these machines, from engineers like Thomas Brennan to nameless water boys, endured danger, exhaustion, and hardship we'd find intolerable today. They worked without labor protections, safety regulations, or insurance. When they died or were maimed, their families often received nothing. Their sacrifice, sometimes literal, powered agricultural expansion that fed growing populations but rarely enriched the workers themselves. Yet many who survived remembered those years with pride and even affection. The satisfaction of competent work well done, the camaraderie of shared effort, the mastery of complex machines. These provided meaning that transcended hardship. Reading accounts by elderly ex-engineers, you find not primarily complaints, but nostalgia, memories of dawn startups, the satisfaction of smooth operation, the pride of reputation earned through skill. Modern preservation efforts honor this memory while avoiding false nostalgia. The best steam demonstrations present complete pictures: the achievement and the danger, the innovation and the exhaustion, the community and the tragedy. They invite visitors to appreciate both what was gained and what was lost: connection to machinery's physical reality, understanding of power source, awareness that comfort and convenience always have costs. The technical achievement remains impressive. That J.I. Case and contemporaries transformed factory stationary engines into mobile, farmer-operable power plants safely enough for widespread adoption represented engineering innovation equal to any modern breakthrough. They worked without computer modeling, finite element analysis, or advanced material science, relying instead on empirical testing, careful observation, and incremental improvement. Their success created an industry, transformed agriculture, and demonstrated engineering's power to reshape society. The Case portable steam engine of 1869 was both ending and beginning, last expression of purely mechanical power generation, first practical mobile power plant. It bridged eras, connecting traditional agriculture to industrial farming, individual craftsmanship to mass production, animal power to mechanical. Understanding this machine means understanding the pivot point where America transformed from predominantly agricultural to industrial, where human muscle began its long displacement by mechanical power. Every combine harvester operating today, every tractor pulling implements, every mobile generator powering construction sites, all inherit DNA from those early portable steam engines. The engineers who perfected them, the farmers who adopted them, and the crews who operated them laid foundations we still build upon. The steam whistle that once announced the engine's arrival across fields has long since fallen silent, but its echo persists in every mechanical heartbeat of modern agriculture. We owe them memory, understanding, and the recognition that our comfort was built on their courage, ingenuity, and sacrifice.